Hi, I'm Dave Goldsman, a professor in the School of Industrial and Systems Engineering at Georgia Tech, and I'll be talking about some powerful uses of mathematics in industrial engineering and operations research. There aren't many easy problems out there in the real world, and industrial engineers need some pretty sophisticated mathematical tools in the modern workplace. First, let's begin with a simple experiment, flipping a coin. Let's suppose every time I toss heads, I earn $1, and every time I toss tails, I lose $1. Where do my total winnings stand after, say, 10 tosses, 100 tosses, 1,000,000 tosses? Such an experiment is called a random walk. Think of me taking a step to the right every time I earn $1, and a step to the left every time I lose $1. In terms of my experiment, I'd like to know where I'm going to end up. But why is something like this of importance to people in ISyE? Well, if you increase the number of steps in the random walk, it converges to a process called Brownian Motion. Have you ever seen anything like this example of Brownian Motion before? Sure, take a look at IBM's stock price over the last year. In fact, many financial engineers use Brownian Motion to model stocks, options, and other financial instruments. Brownian Motion is so important and mathematically deep that at least 2 scientists have won Nobel Prizes explaining it and using it in all sorts of applications. In ISyE, researchers use Brownian Motion to study a variety of things, like what goes on in busy queuing systems, or how to develop efficient quality control charts, or of course in modeling stock and option prices. As a second example of mathematics used in our field, let's talk about something that almost every sports fan can relate to, namely, who's going to win the NCAA basketball championship this year? This is a tough problem that involves a number of aspects of probability, statistics, and optimization. The goal is to somehow use our analytical skills from these mathematical areas, along with some intelligent data mining, to make reasonable predictions, and hopefully to win our office pools. In terms of data mining, there's certainly a lot of information out there. For instance, how much of a home court advantage is there? Are the teams currently on a hot streak? And can a team's margin of victory give us any clues about future performance? NCAA tournament prediction is clearly an active area, both from a seat-of-the-pants perspective and from an analytical perspective. We're very lucky in ISyE to have researchers who've developed an extremely successful prediction technology called the Logistic Regression Markov Chain method. What's really nice about this ranking system is that it's designed to use only basic scoreboard data. For instance, which teams played, whose court they played on, and what the margin of victory was, though there's also a Bayesian add-on that allows a gut feeling to be put into the equation. Obviously, you have to go out and play the game, so you can't predict things correctly all the time, but our system has done very well compared to just about any other prediction technology. A third example involving mathematics and modeling in ISyE concerns the important problem of disease propagation. In 2009 and 2010, the Northern Hemisphere had to cope with the first waves of a new swine flu pandemic. Despite high-profile vaccination campaigns in many countries, delays in the administration of the programs were common, and so high levels of coverage weren't achieved and the disease wasn't effectively controlled. We were lucky. This strain of swine flu wasn't so bad in terms of mortality. In fact, it wasn't much worse than regular seasonal flu. Next time we might not be so lucky. So what can be done to stem the march of a pandemic disease through the population? ISyE researchers have used a variety of mathematical tools to model the disease, as well as certain mitigation strategies. These tools include the use of probability, statistics, differential equations, and optimization, which are then used in conjunction with computer simulations to come up with strategies for mitigation. What kinds of strategies are out there? Here are a few possibilities. School closure and social distancing, that is, keeping people away from each other, especially sick little kids. More reliable vaccination supply chains and compliance, and placement of more effective resources in locations that will allow healthcare officials to respond optimally to a pandemic. Obviously, some of these strategies cost a great deal of money, and some work better than others. ISyE researchers are interested in optimizing healthcare outcomes and are actively working in this area. One nice thing about all this work is that it can be extended to other arenas. For instance, measles, malaria, cholera, and even, believe it or not, zombie attacks. I've only had a chance to talk about a few random examples about the power of mathematics in industrial engineering and operations research. I've only just scratched the surface. If you'd like more information, go to www.isye.gatech.edu.